Okay, I might splice that someday, but we'll just keep on going here. Exploring the elevator, really rich. It takes some training. Use the method. You will get in trouble if you have a knee-jerk answer. If you lay it out, the answer will be there, and if you check with your intuition, it'll actually make sense, but it'll probably be different than you would have initially responded. You're betting $1,000 on every one of these questions, so pause and get it right. We started with moving upward. The acceleration is 0, then that means, in this case, n is balancing mg. If I'm increasing speed, then the upward force, namely n, has to be greater than mg. If I'm moving up and decreasing speed, then in that case n has to be less than mg. And you feel it. Get in an elevator and feel it. Write it out. There's only two forces, and you've got them equal to mg. Again, be careful with which direction you call positive or negative. It doesn't matter, but just be consistent, and your answer will come out. Now let's imagine the case where the elevator is moving down. Well, if you're moving down, can the acceleration be 0? Sure. You're just traveling again in dynamic moving. Equilibrium, acceleration is 0. Acceleration is 0, forces are balanced. In this case, forces are balanced. N has to be equivalent to mg, and your scale works. Your scale works. Fine. What if the acceleration is positive, namely up? Well, if you're moving down and the acceleration is up, you have to be decreasing speed, right? The acceleration's up. Forget about this. If the acceleration's up, in either case, the upward force has to be more, and n is then greater than mg. So n being greater than mg just tells you the acceleration is up. It doesn't tell you whether you're going up and increasing speed or going down and decreasing speed. So this is really good, and it's great. The method will get you the answer. You don't have to knee-jerk get it. You don't have to solve these things without laying the puzzle pieces out. You don't have to throw the puzzle pieces down and just see the answer. Don't do it. The mistakes are too costly. So last case. Negative, meaning down. What's going on? And what's the case? You figure that out. All right? So that's a nice, rich problem. Is the normal force the same as mg? No. Is the normal force a force of gravity? No. It's not even the same here. It's the same strength. They balance. This is from the surface. This is from the entire Earth. Right? So be careful. Put them in as separate. They go on the left side of the equation. I like to work vertically like this. All my actual pushes and pulls here in my table, I put them in the x, break them into x components and y components. Sum of the force x equals max. Sum of the force y is equal to may. And you're good. This is not a force. These are all the interactions. Cool. Now, one last bit, and then you can do lots of problems. Maybe I'll go here real quick, just so I don't forget. As an inclined surface, if here's my R, my receiver, there's an inclined surface. I don't know which way it's moving. I don't know how much friction it is. I don't know. But what direction is the normal force? I got to do a free body diagram. Normal force is perpendicular and away from my surface. And so if you want, take your hand and make it like that. And use purple for perpendicular. And you're good. It's like that. 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 It's perpendicular and away. So my picture is shot. But the normal force is there. And we're good. What direction is gravity? Well, gravity is straight down and vertically down. In other words, and vertically down, by the way, means toward the center of Earth. So down is this way. That's what down means, right? Down. And so if you got a ground here and you got vertical, there it is, and that's the mass of the receiver times g. Is g the acceleration? No, it's not the acceleration. Of course it's not. This is the strength of the force of gravity for reasons which we've seen and derived. So that is the strength of the force of gravity. That is the normal force. I don't know what it is. I don't know what the other forces are. Whether I got ropes, I got all kinds of things. So just put it in. N is N, mg is mg. What the resulting acceleration is to be seen. So that brings us to the last little point here, and then you can read your texts and work with your professor and so on, and work with your classmates to sort it all out. That is, what does the word weight mean? Weight. Weight. What does weight mean? Personally, my suggestion is don't even use it, but books will. Sometimes instead of force of gravity, they'll use the letter W. They might use W with an arrow. The reason that I say at least be careful is that there are some books that use the word weight one way and then later use it for something else. Let's straighten that out. Weight. There was a poll of physics professors, and most of us agreed that we would like the word weight to mean force of gravity. So which we know is in magnitude mg down, right? That's how much weight is. It doesn't matter what you're doing. You can be accelerating up, accelerating down, free flight, sideways, anything hanging on a string, springs, friction. Still, the force of gravity is mg down. That would be your weight. Now, your scale is going to read something different, as we said last time. So if your scale accelerates up, all of a sudden it's going to look like you weigh more or less. The scale would say more or less. More, right? Because it's got to push harder to accelerate you up. Now, I don't know if that means I'm moving up or down, right? Really work on this little thing, and you'll have a lot sorted out. Okay, so the scale says more, but did my mass change? Did the force of gravity, the force that Earth, all pieces of Earth from here to China pull on me, did that change? This doesn't change. This is independent of your motion. Let's write that. Independent. The only requirement here is that you're near the surface of Earth, so you don't have to worry too much about it. The other thing that weight can mean is the force from the scale, or what the scale reads, which in most cases is a normal force or a spring force. Now, acceleration 0 and velocity 0. I can accelerate, I can move at a constant speed, acceleration 0. I can move at a constant speed, acceleration 0. And the scale balances mg, so the scale is equal in strength to mg, very different types of forces. But if I try to accelerate up and then accelerate down, the scale changes. Just exactly in this way. So the scale force, if I use weight as the scale force, then that's variable. That depends on the acceleration. It depends on the acceleration. Here, whatever you're doing, accelerating or not, the Earth is pulling you the same. But this depends on the acceleration. So to call weight the scale force, my solution would be call this force of gravity and call this scale force. Put them in. They're separate phenomena. Get rid of, abolish the word weight. The only trouble with that is people use it. And most times they're talking about this because they don't even know this and they haven't studied this. But in some books, again, they go back and forth. Now, a more careful book would say, call this the apparent weight. So when they ask for the apparent weight, they're looking at the force from the scale, which is either a normal force or some spring force here from the scale. So just put it in like this and solve for that. That's what they're looking for. Okay? If they want the apparent weight, then they've spoken pretty carefully. If they said scale force, then you'd know, again, in this case or this case, we're standing on a scale. You just put it in as a normal, or just a force from the scale. Put it in with everything else. There could be millions of forces. Well, that would be pretty unreasonable. Tension, springs, friction, normal, that whole list. And you just want to know what the scale is telling you. But Earth doesn't really care because it's going to just keep on pulling somehow, some way, mysteriously, in a way that we aren't going to worry about for now, mg down, the force of gravity. Not a normal force, not a scale force, not a contact force, a strange force, mysterious, wonderful force of gravity. G, not the acceleration, except in free flight. Mg, the force of gravity, independent of your acceleration, and certainly all of this independent of your velocity. So I think you're in great shape now. We've got a couple more examples to look at. How are we doing? Left? All right, let's do something else then. Now we really start using our method. Ultimately, you've got to do it yourself and think it through. So if you don't want to mimic solutions, it's harder. Initially, learning this stuff is tricky, and you really have to think physically. But in the end, you'll have something. If you mimic solutions, you might get a passing grade. In a bad class, you get a B, or horrible if you get an A. But if you think physically, it's going to start being more comfortable and much more fun. So push yourself to walk yourself through that thinking process and thinking physics and seeing physics, laying it out. That's rich and going to prepare you for upper division engineering and so on. You can do this. You can do this. It's a fun puzzle. Enjoy the puzzle. Okay. Let's take it. So now we've got force of gravity is mg in most cases for the starter course, and for most cases it's mg. Great. We've got our steps over here. So let's take a look at some other problems. Remember, you can do force analysis, and then you can throw in some kinematics analysis if you want to know about velocity, time, displacement. Then you've got kinematics likely at this point. Suppose you have, these are some classic problems. I won't do them all for you because, again, it may seem more comfortable. Oh yeah, I know how to do that problem. You haven't learned it. Right? More than likely, your professor's going to throw you a little curveball, which you can handle and knock out of the park if you follow the steps. So let's just look at some cases. Suppose, let's take a horizontal surface here. Let's take 2 or 3 objects kind of like this. I don't know my magnets. That's fun. Or anything. You know, you can have this, or you can have a kind of like, let's put a B for blue and G for green and R for red. And here's our case. And suppose you want to push or pull on them. Now, if you pull, then blue is going to lose contact, right? But you could do this. And this is another variation. So just think the physics. Just pause. Don't see what happens is you think in terms of memorizing, and there's a little variation, and you're going about your memorization. It doesn't fit this problem, maybe. If B is maybe connected, maybe through a rope, or maybe through some other object to G, which is connected to R, like a train, right? Then I could pull B, and R would get pulled. Here I can't unless they're attached in some way. So these are variations. All right, we can do this in one dimension if there's no friction. And we'll see why. So let's say I push F of me, or F of hand, or whatever, it doesn't matter. Okay. And I look at this guy. There's three ways you can approach this, and you only need two because the third is redundant. It's not independent. Okay? So here I go. So what you can do is look at B alone. Choosing the receiver. And then you do a free body diagram on B alone. Okay. You could do G alone. You could do R alone. You could do B and G as one group. You could do G and R as a group. You could do the whole thing as a group. Okay. And what do? You think physically. Put in the forces. Choose a coordinate system. That should start becoming a routine. Take the small steps. I'm going to choose my coordinate system here, and I'm going to call it plus x. If I need a plus y, I'm going to go up here, plus y, but I don't know if I need that yet. AY is equal to, well, you can see physically it's 0. AX is equal to A, I don't know. So you can explore that one. I'm going to now get rid of this. This one's a good problem. Now I've just got B and G. So, how do we do? So the other way we can do this is to treat B and G as a group, B and G. Now I'll tell you the way that I would do it. I would do this and this, or these two. I would definitely do this one. It's going to be easier. Put the forces in it. B feels a force from green. Call it F. I don't know, contact. G feels a force from blue. Same strength, opposite direction. Use the same letter. Use the same letter. Put it in. Right? Free body diagram, free body diagram. Here I just have my force in my hand. It's kind of nice on that whole thing. And we're good. So these are the sorts of things. Follow those steps. Make good choices, and you'll make mistakes and learn from them. Okay, we'll continue on.